Okay, so we're back on. And then I'd like to switch to this one. And then final thing is that I would like to see from the YouTube how is the streaming. Okay. Looks good. All right. So here is a summary. So, with help of this coordinate partitioning, we can find the relation that is actually very important for us. So we can find the relation between all the generalized coordinates, which is this one here, delta Q, and independent generalized coordinates. Independent. They can be whatever you want. Only really is what is important is the number, how many coordinates can be independent coordinates. And that is number of degrees of freedom. So those things have to match. Okay, so what are the things that I have here? I have here this matrix CDI, and the matrix CDI is the one that comes from this equation. That's the one that combines this relation. And that's, if we go back to this slide, it tells that the CDI is the one that we have dependent part of the Jacobian matrix that is inverted multiplied by independent part. That is telling for any kind of mechanical structure how is kinematically admissible displacement. This result, which just sounds like, okay, so what? Okay, is it making a difference? Yes, it makes a big difference. How it can make a big difference? It can make a big difference because, if we go back to this equation, this concept of virtual work, we're looking the ways to set this concept of virtual work to be equal to 0. And I said that the only way you can set this equal to 0 is when this displacement is kinematically admissible. Now we have it. So we have the way to express it in a way that it is kinematically admissible no matter how is your mechanical system. And of course, it is this way here. So we're going to use this relation here, and once we do that, then we can express equation as shown here. So we have here this part in this Jacobian matrix where we're using coordinate partitioning, and then we have the part that is just matching the dimension. Now we can set this part to be equal to 0, and that's the way we can find the equation of motion. So that's the whole idea. That, by the way, I think it is the most convenient or the most often used way to express the equilibrium. And I'm sure that you haven't heard this method based on Lagrange multipliers before this course. You're more familiar with this one here. I guess so. And now you have these two in a way that it's very systematic. Makes sense? Kind of. Okay, can you be my friend and say it makes sense? Yes, okay, kind of makes sense. All right, so then now this is the whole big picture. Embedded technique, we're dealing with only the few number of coordinates. So we have only the independent coordinates that we are solving. Others we can solve as a post-processing technique. Whereas in augmented formulation we have all the coordinates plus reaction forces. So they are conceptually very different. So this is what we learned, that is, this is based on Lagrange multipliers. So we have to solve every component in a general vector of generalized coordinates and reaction forces. Whereas in embedded technique, it is only the independent coordinates. Which ones are independent? Whatever you wanted to select. Only limitation is that once you do the selection, you have to be able to invert dependent part of the Jacobian matrix. No other limitation. Okay, so that's what it is. So now we're going to use this concept that we're going to practice this first in a static case, and then we're going to use this in a dynamic case. So the big picture is this. This is a concept of virtual work. So it's force, it's going to be force here multiplied by displacement, and now we find the relation such the way that we find the relation between delta R, delta Q. This of course should be Q here. And now the delta Q we can express in such the way that is only independent generalized coordinates. So that's the whole story, and this is how the virtual work now finally look like. And we can already use this in the case of static. So because this part of the equation, we can set that to be equal to 0. And that's the way we can find the static equilibrium. Any thoughts? Okay, you're following me? Or should we start here? No, I'm not going to do that because, it's going to be like torture for you. So let's not do that. Instead, let's look at an example. Example should make this clear for you. Okay? Here's an example. This is a mechanism that we have looked quite many times. Now what I want to do here is that I wanted to solve the static equilibrium. The concept is static equilibrium only. So I'm going to use the concept of virtual work. That's the main idea here. So I'm going to use the concept of virtual work. Oh, hold on. Such the way that the virtual work will be equal than virtual displacement multiplied by force. And now the only force that is applying in this system is a gravity force. And I'm going to follow this whole concept in order to find the static equilibrium. But then you know what's going to happen next. We can actually repeat the whole thing, but no longer in static, but in case of dynamics. So that's what I would like to do here. Okay, so let's get started. So let's first look how is a vector of generalized coordinates. So the vector of generalized coordinates, that consists of 3 components, because we're looking at the one moving body only. And now I have to apologize that the notations are not consistent here. This is supposed to be Rx associated to body. This is supposed to be Ry associated to body. But 1 and 2 are X and Y corresponding. Okay, and then I have this angle theta. And now I'm partitioning these coordinates. So I'm saying that, okay, 2 of these coordinates must be dependent. Which ones? You can do the selection as you want. But I'm just selecting the first 2 to be the dependent. 1 have to be independent. Alright? So my Jacobian matrix that I computed a couple of weeks back, it looks like this. Now I'm going to go to this Jacobian matrix. I'm going to use quite a bit of violence here. I'm going to destroy the Jacobian matrix. I'm going to take this sub matrix here and build their own matrix based on this. And rest will be related to independent part. Okay? Now, by the way, this selection, you see that the selection was actually a really clever selection, because dependent part of the Jacobian matrix must be inverted. And now it turned out to be identity matrix. That's easy to invert that. So even I can do that. So it's going to be identity matrix. Okay, so what I have here is a part of the Jacobian matrix that is independent is first going to be inverted. Then the dependent part will be multiplied by that. So that's how it reads. I have here minus identity matrix, and identity matrix coming from this one here. And then I have this dependent part that is this one here, and I'm ready to find a relation between all the generalized coordinates and independent generalized coordinates. That's how it is. The identity matrix here is matching just to match the dimension. In this case, I have just 1 degrees of freedom in my system, so this is a scalar value equal to 1. Okay. If I would have 2, and then this might have more. Maybe this could have more values then, but now I don't need to have that. Okay. The static equilibrium then. Let's look like how we can first express the generalized forces that are associated to force that is applying in the system. There's only the gravity force here. We know how to do that. So we first express where the force is applying using the equation that we are very much familiar with. And then we're going to differentiate that position with respect to generalized coordinates. All right? So this is my equation. My u bar vector is 0, 0, which simplifies the equation quite a bit, because this part will be neglected, will be deleted. So only thing that is left is R, this translation of the body reference coordinate system. Now it gives us a mapping matrix that is shown here, and this is the external applied forces, which is a gravity force mass multiplied by gravity constant. Okay, and then this is how my forces look when I'm expressing them in terms of generalized coordinates. You still with me? Kind of. Okay, so let's look what happened next. Now this was my concept, so I have here virtual work. I'm using this idea here to express it in terms of generalized coordinates, and then I'm using the coordinate partitioning in order to express that in terms of independent generalized coordinates. And now with all that, that's how it looks. So I have this one here that kind of eliminate the number of coordinates. This is my generalized external applied forces. And finally, when I use all that information, this one here was the generalized inertia, the generalized external applied forces, the one we got a couple slides back. This is my CD matrix, which is shown here. When I multiply this one here with this one here, using this equation that is shown here, I will get just the one equation that I can set to be equal to 0. And the one equation says mass multiplied by gravity constant multiplied by length divided by 2 multiplied by cosine theta is equal to 0. That's when I can find my static equilibrium. When is this equal to 0? This is constant, and the mass is constant, gravity value is constant, the length is a constant. The only one can change is a theta. Cosine theta will be equal to 0 in case of p divided by 2, 3p divided by 2. Too fast, was it? Not too fast. You got the concept. You're not going to say a word to me. That's good. That's very good. That's how it's supposed to be. Because, otherwise you will give those clever questions and comments, and then my kids are no longer able to see the lunch. All the lunch that goes to you then. They will be very sad. Okay. Well, you can ask it. You can ask. Is it clear? Makes sense? Makes sense. I think so too. Makes sense. Okay, the final step. Let's move on and make this in the case of dynamics. Of course, this all happened quite fast, and I'm sure you need to do, what you need to do is that you need to go back and forth in the recording and see this again. But the idea is quite clear. It is based on the coordinate partition. Maybe it would be nice to make an exercise such that you don't select theta as an independent coordinate, but you select, say, r, where's my writing here, ry as an independent coordinate. So then the dependent part would be this one here and this one here. So the dependent part of the Jacobian matrix would be, in that case, like 2 by 2 matrix, like this. L divided by 2 sine theta, L divided by 2 cosine theta. This would be my independent part. Now inverting that, still possible, but no longer straightforward. And then everything else should be like that, just to see how it goes. We're not going to do that exercise here, but if you're curious, that would be a nice thing to do. Think about like next weekend. Have any special things to do? Here it is. You can practice this. No need to go to the bar. You can save some serious money. And it's fun too. Kind of fun. Okay. Now, like I say, let's move on and let's hold on. Let's extend this to dynamics. Okay, so we are very close to that. So that only needs a few steps, and then we are done here. And the steps, this is our concept when we use the virtual work in case of dynamics. In case of dynamics, remember there's additional component in addition to external applied forces. And that additional component was inertia forces. Correct. And we express the inertia forces in terms of generalized coordinates. And we end up to have mass multiplied by acceleration minus quadratic velocity vector. This is external applied forces. This is the one we use in case of static. Now in dynamics, we have this extra component. It's like this guy. You know, this is what we used in the case of static. Now in the case of dynamics, we have to account these two components. So it's not enough to use only external applied forces, but we also have to look at the inertia forces. All right. And when we use the concept of virtual work for this combination, we end up to have this. And we concluded that we cannot set this to be equal to 0, because virtual displacement, this guy here, may not be kinematically admissible. But now we learn that we have the way to express it in a way that is kinematically admissible. And is this relation shown here. So we simply substitute this one here, and then we can say that this equation is equal to 0. End of the story. That's it. So it's that simple. Now this is, when we use this concept, we end up to have very few number of differential equations. How many? That will be equal to the number of degrees of freedom. Okay, there's one more step to take. I wish that is here, but it's not yet here. We still have one more problem to solve. It's not going to be a serious problem anymore, because we already have a big concept that is clear. There's just a minor detail we have to look at. And the detail is this guy here. Oh God, this is an annoying guy. You know what's the problem here? The problem is that it includes all the generalized coordinates. I don't like that. I would like to use only independent generalized coordinates. Okay, so we can make it happen. We can make it happen in such the way that we use coordinate partitioning in position level, velocity level, and acceleration level. That's the idea. That's what we have to follow. Problem what comes in when we're using the coordinate partitioning in acceleration level is that it's mathematically quite involving. It's a mess. But the only idea, what I'm trying to do here, is that I wanted to find a similar relation than in the position level, like this one here, but now in acceleration level. It's a little bit of a mess, but once I'm done with that, then I can express the equation of motion using very few number of differential equations. And then we will practice. Okay. Now, this is a little bit of explanation. It simply says that this is still a component that is difficult. We cannot use it as it is, but we have to introduce a coordinate partitioning in acceleration level. When you look at the acceleration level, this is what we have to deal with. So it's a acceleration multiplied by Jacobian matrix. All this is what we have to deal with. And now when we introduce coordinate partitioning to this level, it needs some, it's a little bit of ugly business. So it basically goes in such the way that, you know, I'm expressing the coordinates in such the way that I have dependent coordinates here, and the dependent coordinates are actually, let me get started here. So I have here dependent acceleration and independent acceleration. Now those are related to the CDI, which we are already familiar with, and then we also have something that is called CD, and the CD is coming from this equation. CDI, it's quite straightforward. That's the one we used in the past. Now the new component is this CD, and it's coming here. Okay, without further details, let's call this component in a certain names. And you know that what we're going to do then is that we're going to express all the generalized coordinates in acceleration level and independent accelerations. And now we're going to call these components in a certain way such that this one here, which we are already familiar with, will be called as a B. This one here, that was an additional component, that's what we're going to call as a D. Now we're ready to go and do this substitution. Substitute this one here to this guy here. And when we do that, the final equation of motion look like this. is a mess. But still, this is, if you have a system that consists of, let's go back to like this crankshaft mechanism. The crankshaft mechanism, remember this one here, so we have 1, 2, 3 moving bodies. So that will be a total of 9 generalized coordinates, correct? Okay, 9 generalized coordinates. And then I have here 1, 2, 3 revolute joints. Excuse me, this should be minus. So it's 2 multiplied by 3 plus translational joint here 2. So that's 8. So it's, let me write it here, 9 minus 8, that's going to be 1. 1 degrees of freedom in the system. So when you're using this substitution technique, you will end up to have one differential equation to solve the response. Whereas if you're using the method based on Lagrange multipliers, you will have same number, 9, 8, but plus between. So it's going to be 17 unknowns. 17 versus 1. Okay, that's what is this other method, alternative method. Which one is better? Depends where you look at that. There is a, the multi-body community kind of is like, there's like American community and the European community. And the Europeans, they prefer the method, well, this is very rough speaking, but still, the Europeans, they prefer this method where you end up to have very few number of differential equations. Americans, they prefer the method that is very straightforward but end up to have very high number of unknowns. My background and my supervisor is from the United States. So which one we vote here? So we vote for this one. Honestly, doesn't really make any difference. So you pick the one you like the most. But I'm a fan of this method because of my supervisor. No other explanation, because otherwise it makes no really sense. But you may thought that this method here is superior because it leads to so few number of differential equations. Correct. But it's based on the coordinate partitioning, which itself is quite CPU consuming concept. So really depends on the application. Hard to say. Sometimes this is more efficient, sometimes this. It really depends on your application and your preferences. What is it you like? Okay, so this again, summary, embedded technique, very few number of differential equations, which actually the number of differential equations is actually number of degrees of freedom. Augmented formulation is a lot, but you can get the reaction forces too. In this method, you have to use post-processing techniques to get the reaction forces due to the constraints. Okay, let's look at the one example, and then I'm done for today. Example is the one that we have seen number of times. So it's a one moving body that is constrained by primitive joints in point O, this point here, and point Q, that is this point here. We wanted to create the equation of motion by using substitution technique, embedded formulation. So how it goes. The first question, and the first in-class quiz is, what's going to be the number of unknowns when using this method? Do you know that already? Oh, hold on. In this example, the number of unknowns will be 1, 3, 5, 6. This is all about, what we've been discussing today. Sorry that there are so few in-class quizzes today. Okay, so in this example, the number of unknowns will be now two numbers you need to think. Number of generalized coordinates, number of constraints. And then it's going to be either plus or minus. Or plus or minus, or something else. No, I don't want to make you confused. It is plus or minus. two numbers, you either substitute or you're summing them up. I mean, subtracting them or summing them up. Which one it is? Is it clear? You want to see the mechanism again? So this is a mechanism. So the number, two numbers you need here, number of generalized coordinates, number of constraint equations. You're going to have two numbers, and then you have to do something with these two numbers. But what? You know it already? How is going to be the success rate today? Not 100. More than 100? 100.
81.
That's quite high.
60.
60. I think so too. So, okay, so let's look. Are we ready here? So we have, how many students we have? I think at the exam there were a little more than 100 students participated in the exam. A little more than 100. So today we have, how many students we have in a class? 10. A little more than a 10. By the way, can I ask you, why is that you prefer to come here? Is it easier to follow the lectures here or using the online option? Or is it making any difference? Not making much difference. But I mean, that is all right. You're welcome to be here. Nothing against that. Okay, so we're going to have more students today, more than 36. Okay, I guess that's. Are you all guys? You all done? You done? Okay, 37. So I'm gonna close this in 5, 4, 3, 2, 1. You said 80. What was your guess? 85. Okay. This is the lowest. This is the record so far. Lowest possible. You know, I don't think we ever scored this low. And now we got 43%. But some good news. Very good news here. Okay, let's go back here. So the two numbers we're looking here are the number of generalized coordinates. What's that number? That's 3. Another number we're looking at is a number of constraint equations. That's 2. Now it's all about what is that we're going to put between these two numbers. Minus. Correct. So it's a minus. 1 is the correct answer. This is a correct answer. So it's a minus. In the alternative technique, which is this augmented formulation, it would be 3 plus 2, 5. Many of you voted this one, but it's not this method. This method gives you only one differential equation. Only one. Okay, so let's practice. So let's again use these steps. Now once I'm done with these steps, then I'm also done with the multi-body system dynamics. So then that's it. Then we're going to move on to hydraulics. The next week is going to be about the hydraulics. The week after that about the hydraulics. Then already I hope to explain something about the gamification concept, game technology, like Unreal Engines and Unities and stuff like that. Then maybe we can play a game together. Some games. We'll see. Okay. So step number 1, construction of mass matrix. Mass matrix, that's we're not going to look at the details because you know how to make it happen. So you know that the mass matrix in this case will be a matrix where the dimensions are 3 by 3. Clear. Because no surprises here. It's going to be very straightforward. So we're going to first calculate the matrix that is associated to translational coordinates. So that's going to be 2 by 2 diagonal matrix. mass of the body is in a diagonal component. And then another component we need is a mass moment of inertia. You can use a pre-calculated tables to make that happen, or you can do the math by yourself, whatever you want. But eventually you get the mass matrix as it is shown here. So it's a 3 by 3 diagonal matrix. The mass of the body is here. This is a mass moment of inertia. Step number 1, done. Okay, step number 2, exactly same than in the case of augmented formulation. So we're going to construct the externally applied forces. This time the only force applying here is a gravity force in this location. So it can be expressed in global coordinates as it is shown here. In global coordinates. In global coordinates the components are 0 and mass multiplied by gravity constant minus direction. Okay, so we first have to look where the force is applying. So it's applying in the origin of the body reference coordinate system, and because of that, vector u bar will be equal to 0. Alright, so we can neglect this component here, and we can get the mapping matrix as exactly in the case of static. So it's going to be this one here, multiplied by forces in global coordinates. What that will give us is the forces in generalized coordinates. How they look, well, it's shown here. These are the forces in generalized coordinates. So why this is not writing? Oh, it's coming. Okay, these are the forces in generalized coordinates. Now that's step number 2, done. Step number 3, quadratic velocity vector. Well, based on the figure here, we can see that the body reference coordinate system is located in the center of the body. So it's going to be equal, the quadratic velocity vector will be equal to 0. Step number 4, not 5. The constraint equations. Constraint vector, QC. And the Jacobian matrix, so QC and the Jacobian matrix, I think this title is supposed to be different because I'm already looking the CD matrix here. So I'm taking the Jacobian matrix of the system, that one. You can take a look at your notes from the 2 weeks back, and I'm using the coordinate partitioning here. And I'm selecting theta to be my independent coordinates. The rest will be dependent coordinates. And now the dependent part of the Jacobian matrix is going to be this one here. And the dependent part, independent part will be this one here. Exactly like in the case of static. Now, once I do with this selection, I'm able to find the relation between the dependent and independent generalized coordinates and all the generalized coordinates, and that all will be based on this coordinate partitioning in Jacobian matrix. So this is what I do, and this is finally how the relation look like. And I'm calling this relation as a matrix B. Alright? Almost there. Now this is right step. So step number 5. Step number 5 is coordinate partitioning in acceleration level. So again, I need this dependent part of the Jacobian matrix, and then I need these components that I use when I calculate the QC in a normal case. And once I actually do that, this I can neglect because of my constraint. The only component that is left is this one here. So it's a Jacobian matrix multiplied by velocity. This will give me a vector of 2 components. That vector I will differentiate with respect to generalized coordinates. It will give me a matrix with 2 rows, 3 columns. And finally I multiply that with the velocity of generalized coordinates. And then I will do all the substitution. And I'm ready to express the D matrix here without showing much of the details. This is how the D matrix look like. I have all the ingredients. If I'm ready to do my final substitution, and my final substitution goes this. So I have the B matrix computed before, mass matrix, which is a 3 by 3, B matrix computed before, independent acceleration. Then I have B again, mass matrix D, B multiplied by quadratic velocity vector, this will be equal to 0, B multiplied by external applied forces, this is how finally my differential equation look like. I haven't made the math, but I'm going to solve this with respect to theta. That's it. What do you say about this? Okay. Yeah, not that bad. So I was, I was like implying that this is like crying and all, it's a miserable thing to explain this. Did you find it useful? Hard to say. But I hope that when you look back to your notes in Dynamics 1 or Dynamics 2, many of you have heard this concept of virtual work. And I'm quite convinced that many of you have never understood the concept correctly. But I don't know, again, it's clear if you have now the clear understanding, hopefully you will get this idea about kinematically admissible displacement, because it's a very, very central ingredient in that concept. Okay, embedded technique versus augmented formulation. Embedded technique equations are based on coordinate partitioning. That's the key component here. And the equations do not include the reaction forces. Only very few number of differential equations are needed. Augmented formulation, large number of equations and unknowns. That's what it is. Equations of motion are relatively simple. That's a vague statement, so it's hard to say anything about that. Reaction forces are included in the equation of motion. That's clearly a positive thing. And my final slide today is a tip for mechanical modeling. Is to verify your model frequently, no matter what is the method you're using. Be aware of number of degrees of freedom. And I will get back to the simulation assignment. I will give you some hints how to accomplish that. But my first hint is get started this week, because Christmas is coming soon, and it's good to prepare the model and submit it already as soon as you can. And something that is quite important is that make sure you understand the physical meaning of all the parameters in your model. So it's not about shooting around and trying an error. The modeling is not about that. You must be aware of what you do, and it includes all the details. So if you enter the parameter, you must understand what this parameter is standing for. And then, this is a minor detail, but don't ever merge the rigid bodies by a fixed joint, because whenever you're using this method based on Lagrange multipliers, you just keep on adding the unknowns, and that's not the good policy. Analyze and visualize your model frequently during the modeling phase. Before dynamic analysis, try to find the static equilibrium. That's quite critical. Think, and think, rather than do. I remember, some years back I was involved to these guided tutorials. Some of the students, they were really, really fast. I mean, the frequency when they clicked the mouse, I think the frequency was like 50 hertz. They were really like this speed. But oh my God, what a mess they were able to create. Nothing productive, but a mess. So it's not about how frequently you can click your mouse, but how much you can do the thinking. It's all about that. All right, with that, I promise that let's close for the day. Let's close for the day. And what will happen on Tuesday then is this. So we're going to move on to hydraulics. We will get started from the properties of fluid. We'll look at how is alarm fluid theory, flow types, all that. So completely new topic. So subject matter, in my opinion, for many of the students feels that it's more pleasant than multibody dynamics. I personally prefer multibody dynamics, but either way, so both we will cover in this course. Okay, let's go back home and let me close the streaming and recording.